we'll go from current slide. Sorry, we're a little late getting started. I had just stacks of students after the last class and didn't get them all out of here until 8 minutes after, and then I had to run down to my office for a little bit. So, any questions on anything we've covered so far? Okay, we are in section 8.7, integration by tables and other integration techniques. And we did example 1 last time, and we're getting ready to start example 2. And let me just, okay. Example 2 isn't listed. That's what I thought it was, but I want to make sure. However, example 2 is, you can find at larsoncalculus.com an interactive version of this type of an example. If not this exact example, you should be able to get it. So let's see what we can do with this. Let me get my pen set up, and we'll go from here. Here's example 2. Find this. The integral of x times the square root of x to the 4th minus 9 dx. Okay. Now, where would you go for a problem like that? What would be your approach? If that had been a square there, substitution would be pretty easy, right? It's not, okay? So, without much of else that you can think of doing, and I can think of doing, let's head to the tables and see what we can get there. Okay? And again, I'm not as familiar with this book as I am the others. They make the tables really hard to find here. Here we go. The last numbered page in the text is 1128, okay? Then begin the appendices, and rather than numbering them consecutively, they're numbered A's and B's and stuff like that. So to find them, you have to find the end of the text, and then that's where your integration tables begin. There's actually the first appendix is proofs of selected theorems, and there's just a couple there, okay? But then the integration tables begin. All right, and that's what we're looking for, something that looks like that. And this is not a form that involves A plus BU. Not quite, okay? Nor is it A plus BU plus CU squared. It kind of looks like square root of A plus BU, but it's to an upper power. So we'll hold off on that for a moment. It looks more like square root of U squared plus or minus A squared, except it's not a square. But I think that's where we need to hang on to. If you keep looking, you don't see anything that comes any closer, right? So, let's go to that form that they have here. Okay. All right. The intern returns. Okay. Find you there, will you? All right. Anyone else come in since I called her? Good deal. Okay. We're doing. Thank you.
I accidentally put number 3 where number 2 is, but I drew the arrow.
You did what now?
I mixed up the places.
Okay, you're just trying to confuse me, right? Okay, I got it. Thank you. I'll usually figure them out. Usually. Okay. Okay. Now, the closest thing that we see so far is that square root of u squared plus or minus a squared. Okay? And in those, that's 26 through on. And right off the top, I would say let's try to use 26, but let's see what we might be able to do with that. Okay? Let's to get it to look closer to what we've got there, let's let u equal x squared. What would that do for us? Okay? The first thing you would then say is du is equal to 2x dx, right? Okay? Now, with that in mind, our new integral would then be, let's fiddle with that a little bit, let's divide both sides by 2. So x dx is equal to 1/2 u du. Well, getting this into, put the 1/2 on the outside, and then you have the square root of, and if u is equal to x squared, then that would lead u squared to be x to the 4th, right? Okay? So what we would have then is the square root of u squared minus 9 du. Wouldn't it? Okay. Now, that is exactly what 26 is, or sort of close to it, right? You see it? Okay. And 26 tells you, this is from the integration table at the end of the thing, the integral of, and you could do this without using the table, u squared minus a squared du is equal to 1/2 u times square root of u squared minus a squared. Okay. Plus, let's see, plus, this is going to be a minus a squared times the log, natural log of absolute value, u plus, boy, what a problem, u plus the square root of u squared minus a squared. Okay? And then we have our plus c. Okay. That's what that turns out to be. Now, in our case, the a is equal to 3, right? So a is equal to 3. So we have 1/2, and let's put them in. You got another 1/2 from your result here. U, and let's go on, and I think it's okay to, let's make that u x squared, because that's what that is, times the square root of u to the 4th minus 9, x to the 4th minus 9, minus a squared, which is 9, times the log of x squared, u is equal to x squared, and make sure I didn't do something stupid there. Yeah. Absolute value x squared plus the square root of x to the 4th minus 9 Well, that's an absolute value there, plus C. Okay. All right. So what would this be? 1/4 x squared times the square root of x to the 4th minus 9 minus 9/2 log absolute value x squared plus the square root of x 4th minus 9 plus C. Now, couple things to note. Well, no, I was starting to say that I'm pretty sure this is always going to be greater than that. Okay? With that being the case, you can probably replace that and put parentheses rather than absolute value bars. But that's not really a major point there. Terrell is here. Okay. Now, with that in mind, let's go back and see how we did. 1/4 x squared on the square root of x 4th minus 9 minus 9. Oh, they have the 1/4 on the outside. And everything else looks okay, except I may be off by a factor of 2 in there, and I can't quite see why that's the case. I'm not sure they don't have their fraction in the wrong place. It seems like to me it's either a 1/2 on the outside, if I'm looking at their table right. No, I'm sorry. That 1/2 was completely outside that. Sorry. They're right. So this will just be a 9 there. If you put the 1/4 on the outside. Yeah. That's right. I thought the 1/4 was, or 1/2 was just in front of the U, but it's in front of the whole term there. Sorry, I misread my parentheses. So yeah. So sometimes, even to get to the table, you need to do a substitution. Okay, can't do the final part at all, but to get to a part that you can use from the table, you need to do a substitution to get it look more like the table. So that was the example of that. And these are a little on the hairy side sometimes. I'll try to keep some pieces of paper back there and some up here. All right, any questions on that? Let's try example 3. Okay, looks like a fairly straightforward. But this is a definite integral from 0 to 2 of x over 1 plus e to the minus x dx. Okay. Oh, x squared, you're right. I just noticed that. Okay. Now, at first glance, it looks like we might be able to do a substitution, wouldn't it? Okay? Let u equal either x squared or minus x squared. So let's try it. What you want to do, x squared or minus x squared, I don't really care. Pick one. Minus. Okay, let's try this first. Let u equal minus x squared. Then du is equal to, second, negative 2x dx. Well, we have a x dx, so let's get rid of the minus 2 by dividing that out. And now we have the integral from, well, let's see. Let's leave off the limits for now, okay? We'll come back and take a look at those if it works out. I don't want to get through all that and find out. And we'll have a minus 1/2 out front, okay? And then what do we have? du over 1 plus e to the u, right? Still a problem, right? Nothing, let's see. I don't think that's going to help us much. So since that didn't provide much relief, let's go to the back. And again, let's start looking at the titles here. And forms involving u to the n, a plus bu. None of these are helpful because there's no e's involved. Here we go. 81 through 86 are forms involving e to the u. Okay? Look at number 84. 84 is exactly what we've got here. Okay? So yes, what we did was useful, helpful. So we are going to use it. Now, at this point, since that is useful and helpful, let's go in and plug in our values. If u was minus x squared, when x is 0, u would have been 0, okay? And if x was 2, u would have been -4, okay? I really don't like to have the minus here, so what I'm going to do is reverse those and make it a 1/2, the integral from -4 to 0, of du over 1 plus, goodness, my writing stinks. No. Okay. 1 plus e to the u du. Okay? Now, that's a 1/2. That's from our preliminary stuff. Now let's plug in what number 84 tells you it is. That's u minus log of 1 plus e to the u, and then they do a plus c. We don't need to do the plus c. We plug in 0, -4 to 0, okay, into our u. And what does this become? Is anyone else coming into this call roll? All right, let's plug it and see what we get. I'm going to come up here and do it. 1/2, 0 minus the log of 1 plus e to the 0. E to the 0 is 1, so it's log of 2 minus a -4. Watch these signs, folks. They can sneak out here and trip you up big time. Yuck. Okay. -4, and I'm going to put the minus here, though the minuses will take care of themselves in a minute, the log of 1 plus e to the minus 4. Okay, which is 1/2 times minus log 2 plus 4 plus log of 1 plus e to the minus 4. I think that's about as far as we can take it. Maybe one more step. 1/2 4 plus ln of 1 plus e to the minus 4 over 2. I don't know if they take it that extra step. Let's see. 1/2 4 plus log, no they don't, but you know, it's still okay. Log of 1 plus e to the minus 4 minus log 2. They just do it at the end. And then they use their calculators and give an approximate answer about 1.66. Okay? And then they show the graph of that, which I was not about to graph, but it's a fairly interesting looking little triangle there. Not quite a triangle, but close to it. And that's approximately the area represented by that image. Okay. Now, any questions on those? So it's a lot of insight. Try a thing or two, see if it works. If it doesn't, try something else. And sure enough, you ultimately should get to an answer. Use the tables. Some things you just can't solve without them. Okay. So let's move on, and if there are no questions, now let's look at reduction formulas. And you'll see these in tables too, and sometimes they look fairly simple until you start having to use them again and again and again. Several of the integrals in the integration tables have the form of the integral of f of x dx is some function g of x plus some other integral of h of x dx. Okay? Now, you still don't know the answer, okay, because you don't know what that one is. Unless this is a form that's somewhat similar to this one, and then you just carry it through again and again until you get down to a form of something you can do. Such integrals are called reduction formulas because we reduce a given integral to the sum of a function in a simpler integral. There's the key. That next one needs to be simple. Okay? Here's an example of that. Find the integral of x cubed sine x dx. Now, wait a minute. We should be able to do this, shouldn't we? What would be your first thoughts on this? Any thoughts on this? Your last thoughts on this, okay? That to me smacks of it's a product, and what technique that we have that derived itself from the product rule. Integration by parts, exactly. So I'm not sure I would even go to the table on this. Let's just see. What would integration by parts tell you to do? X cubed and dv equal to sine x dx, sorry. The old gray cells aren't working too well today, sorry. Now, here's the thing on integration by parts. Pick the one, the u, to be something that's going to be simpler when you differentiate it, and the dv to be something that doesn't get that much more complicated when you integrate it, right? And that's going to be the case there and here, right? So what would we do? What would be your next step? Then, you tell me. du is equal to 3x dx, and v would equal to cosine, negative cosine x, right? What's that? Yeah, I'm sorry, 3x squared dx, sorry. Like I said, the old gray cells aren't working well this morning. Yeah. So this would be 3x squared dx, and that would be minus cosine x, right? So the derivative of minus cosine is positive sine, right? Okay. So, then where do we go from there? Integration by parts says to take the u times v, which is a minus x cubed cosine x, and then subtract from that the bottom line here, the integral of that. Well, the minus is going to make that a plus, and this will be a 3x squared cosine x dx, right? Everybody agree or not? Okay. Now, things just got incrementally better, but better. Now we've got an integral over there that we still need to do something with, and what do you think we should do with that one? Same type thing. Let u equal, and now if you don't like using the same variable, make up a new variable. Well, I don't mind using it, so let's go for it. And that would be x squared, right? And dv is equal to cosine x dx, right? Then du is equal to 2x dx, and v is equal to sine x. All right? Now at this point, let's not forget our original part, minus x cubed cosine x. Okay? And then we'll do the product here, and that's going to be a plus 3. Don't forget the 3, it's there. X squared sine x. Okay? Minus, and the 3 still in front of that, so I'm going to put that there again, the bottom line here, and that's going to be another 2, so that's going to be a 6 times the integral of x sine x dx, I think. Okay? Everybody in agreement so far? Okay. One more step to go. Well, at least one more step to go. Don't forget these. Minus x cubed cosine x plus 3x squared sine x minus, okay, 6. Now what are we going to do with that one? Oh wait, yeah, okay. I think we've got everything covered. One more time, okay? This is going to be let u equal x, dv equal sine x dx, okay? Then du is equal to dx, and v is equal to minus cosine x, right? Yay or nay? Got it? Okay. So this will be a minus x cubed cosine x plus 3x squared sine x minus 6 times uv, and that's going to be a minus, so that's going to be a plus 6x cosine x. Then the bottom line, again a minus is going to be a 6 times the integral of cosine x dx. Now what is the interval of cosine x dx? Negative sign. All right, so this then, I think this is the last go here, minus x cubed cosine x plus 3x squared sine x plus 6x cosine x plus 6 minus 6. You just said minus and I put plus. Okay, minus 6 sine x. One last thing, plus c. Okay. Now, maybe it would have been easier using a table, but it wasn't that bad just doing it. Minus x cubed cosine x plus 3x squared sine x plus 6x cosine x minus 6x, 6 sine x plus c. So there was really no need for a table, and I'm not sure the table would have helped us that much anyway. By the time you go back and substitute in like crazy. Let's see, I'll let you make the call on that. All right, to erase? Anybody need it still? Okay. All right, let's see how they did it. It said, consider the three formulas listed below. The integral of u sine u du, which is that, formula 52. You could have got that straight from integration by parts. Integral of u to the n sine u du, and that would have given you this, and there is your reduction formula. So why, well, I guess you do ultimately will need this, but this one, the integral here, that is exactly what we've got here, where your u will be x, no, the n will be 3, okay? So that will be minus x cubed cosine u plus 3 times the integral of this, which you go back and plug back into this one. Well, no, then you use the cosine one, which this will be the cosine one. Plug that back in, okay? And then one more time, you'll plug in the last one. Oh, no, they're showing this. That's plugging in the first time, plugging in the second time, and then going back to the first one they listed and plugging in the third time, and yeah, you got it. Now, I don't know. To me, that seemed like just as long as doing integration by parts 3 times. But pay your money and take your choice. You've already paid your money. You take your choice. Use the tables and try to keep up with all the various things in the table, or integration by parts. Either one would do. All right. So that was a pretty straightforward one. That was example 4. Any questions on that? Okay. They skip example 5. So let's back up and do example 5. Find this integral. This looks like a real wiener. The square root of 3 minus 5x over 2x dx. All right. Now, that really looks like a pain in the neck, okay? Usually you think of whatever's in the denominator is going to be the more complicated part, but usually you also think of whatever's on the square root is going to be a more complicated part. And now what's in the denominator isn't what's in the square root. They've got them reversed, and that really becomes a real pill, okay? So one option will be go to your tables and see if you see anything that comes out close. Okay? Okay. And yeah, possibly number 19. It has some stretch of the imagination that it might be somewhat related. I'm going to write down 19 for you. The integral of square root of a plus bu over u du. Okay? Now, to get this to look like that, let's first take a 1/2 on the outside. Okay? Now you have an integral of the square root of 3 minus 5x over x dx. Does everybody agree with that? That wasn't that big of a stretch. Just pull the 2 on the outside and you have that. That now is looking very similar to there. Okay? Where the a is 3 and the b is -5. Right? Okay. So let's just sort of jot that down. A is 3, B is -5. All right. Well, let's see what that form tells you the answer is. That form is 2 times the square root of a plus bu plus a times the integral. Oops, here comes the whatever you can't think of the term, reduction form. Yeah, reduction formula. Okay, a times 1 over u times the square root of a plus bu. No, yeah, wait, du. Getting off on a line here. Okay. So that's what it says the answer is. So let's see what we can come up with. All right. 1/2 2 times the square root. Now, the a plus bu is exactly what we've got here, so that's 3 minus 5x. Okay? Don't need to do anything special to it. That's that. Plus a, which is 3, in our case here, times the integral of 1 du over, and your u is x on the square root of 3 minus 5x. Okay. Now, yay, what a big help that was. Okay. Until now you have to go to the table again and see if you can find a square root in the denominator, and that takes you back to number 17. Okay? Now, number 17 has 2 possible answers. One for a's positive and one for a's negative. Well, your a was positive here, so we'll go with that one. Okay? So 1/2 times the 2 times the square root of 3 minus 5x plus 3. Okay? Now this integral is going to be, I hate having all these brackets because they get confused after a while, 1 over the square root of a, which is 1 over root 3, times the log, natural log, of absolute value. Numerator is your square root of 3 minus 5x. Minus the square root of 3, square root of a. Denominator is the square root of 3 minus 5x plus the square root of 3. And then you have your plus c. All right. Now, I'm going to bracket that off there and see if we can clean this up just a little bit. Well, the 1/2 and the 2 are going to get rid of each other, and that's going to be the square root of 3 minus 5x. Okay? Plus, now that can't get rid of the 1/2 there, so that's going to be 3/2. And I'm going to do a 1 over root 3 and just make that a root 3 plus root 3 over 2, the natural log of, and then this, I don't think there's anything you can do to help it, the square root of 3 minus 5x minus root 3, I can't write, minus root 3 over the square root of 3 minus 5x plus root 3 plus c. Now that, I think, is as simple as we can get the answer. Let's see how well or poorly we did on it. Square root of 3 minus 5x, bingo. Oops, can't say that in Alabama, sorry. Plus root 3 over 2, got it. Log of square root of 3 minus 5x minus root 3 over square root of 3 minus 5x plus root 3 plus c, exactly the answer, the form they put the answer in. I can't believe that we agreed on something, okay, but we got it. All right. So again, find something that looks close, go with it. When you get a reduction formula, now that one I would have almost yelled at you and said, that's no simpler, that's as complicated or more complicated, but it's just a different form. You get that one, use that in the table, and sure enough, you come up with a number. There you had an option, whether your A was positive or negative. It happened to be positive, so we used the positive one. And sure enough, came up with an answer that is pretty straightforward. All right. Now, any questions on those? Again, it's almost as much of an art as it is a science. A little more science than art, but here's Corbin. Okay. Now we're moving to rational functions of sine and cosine. Okay? Rational functions. That's a ratio. Something sine or cosine in the numerator, something sine or cosine in the denominator. All right. Here we have one. When you look at something like this, what's the first thing that comes to mind? Second? A trig substitution. What do you mean by that? I think I agree with you. Yes, the double angle formula to get that into say. That's certainly the first thing that pops into my head as well. Now let's see how well the popping goes here. What is sine of 2x? Good idea, but yeah, be helpful. It's 2 times sine x cosine x dx, isn't it? Okay. If you're in any doubt, which you may be, and it's legal to have a doubt, go back to sort of where we came from here. Remember, that came from the sine of alpha plus beta, say, and that was sine alpha cosine beta plus cosine alpha sine beta, right? You remember that? Yeah, okay. And if alpha is equal to beta, then you have sine of 2 alpha, which is 2 times sine alpha cosine beta. Okay. So yeah, I believe that is correct. Okay. If not, just look it up. Okay. That's what we're doing nowadays, is looking up. All right. Now, okay, does that help us much? Doesn't seem like it did too much, at least on first glance. At least you got the same argument everywhere. Now, I'm not sure this is going to be helpful, but it's what I would try next. Especially when you have some type of a sum in a denominator with a sine or a cosine. Change that to the conjugate of that, multiplied by the conjugate of that, and see if that helps any. Now, this may only make things worse, but this is something to try, okay? So what we're going to do is, I'm going to pull the 2 out here, if that's okay. And this will be sine x cosine x over 2 plus cosine x multiplied by 2 minus cosine x. I'm not sure this will be perfectly fine, but let's try it. But if you multiply that, you have to multiply this, 2 minus cosine x, and then dx. All you did is multiply by 1, right? That over that is 1. Okay. Now, it may not help at all, but let's see what it does. That'll be 2 times the integral of, and let's see what the numerator is, 2 sine x cosine x minus sine x cosine squared x dx, right? Multiply this by, each of those by, distribute this across the parentheses, right? Now, what does that denominator become? 4 minus cosine squared x. Now, the whole thing from the beginning that I was in doubt if this would help, and I'm now beginning to be more doubtful it will help. If that was a 1, we're in pretty good shape, right? Because 1 minus cosine squared x would be sine squared x, and then you could cancel out you could do something anyway. But 4 minus cosine squared x, spaghettios, okay? The next thing I would think was maybe make that 3 minus 1 minus cosine squared x. And then that would be a 3 minus sine squared x. And I'm not sure that helps us. We're not much better off than we were. In fact, a little worse off. So even though that was a sort of a good thought, it didn't get us anywhere very useful, I don't think. Okay? But our first step was not bad. It's just that second step didn't do us any good. So let's erase this part. That got us nowhere really quickly. Okay? So let's see what else. Now, this is a bit esoteric, but it still may be helpful. That denominator really looks like a, is that like an A plus BU? Where U is cosine X. I think that's what they're suggesting we do. That's, I think, the closest I'm seeing to much. Yeah, I think that's has to be the one we use, which is one of the simpler forms here. So if we let that be the case, then a substitution is going to be let U equal cosine X, right? Then du is equal to what? Negative sine X dx, right? Well, let's see what we have now. That would be a 2 times the integral of, let's make that a minus 2, pull that minus out front. And what we would have is a u du, u being cosine x, du being sine x dx with the minus out front. And then what we have here is a 2 plus u, right? Okay. Now, looking at number 3, which I think we've used, no, we may not have used it yet. Number 3 looks like that is quite doable. Let me write down what number 3 is. The integral of u du over a plus bu is equal to 1 over b squared times bu minus a times the natural log of a plus bu plus c. Okay? Now, if we're going to use that, our a is obviously 2, and our b is 1. So let's see what we've got. Equals a minus 2, and that integral there would be 1 times u minus 2 log absolute value of 2 plus u plus c. Okay? If indeed that's true, then we can go back and plug in what the u is, which is cosine x. It would be minus 2 times cosine x minus 2 times the log of absolute value 2 plus cosine x plus c. Now, at this point, noticing here, 2 plus cosine x will never be less than minus 1, right? So 2 plus the negative 1 will be 1. So this is always positive. So you can lose the absolute value bars. Okay? So I think that gives you as an answer minus 2 times cosine x minus 2 times the log of 2 plus cosine x plus c. Okay, unless I've pulled up a dumb one somewhere, let's see what we got. Oh, and they actually pull it out. Minus 2 cosine x minus the minus is a plus 4. That's a plus 4, not 4. I'm going to blame that somewhat on my, no, it's just plus 4. Sorry. It's all on me. Okay. Plus 4 times the log of 2 plus cosine x plus c. Okay. So minus 2 cosine x plus 4 times the log. They kept the absolute value bars in there, which I don't think is necessary. I left them off, or I wrote them, but it didn't write plus c. So, good deal. Kind of a bizarre type problem, but, you know, again, sort of strange to think of this as an a plus bu, but it sort of is. As long as your u's and du's will take care of all that. If that hadn't been sine and cosine, you'd have been hurt. But with it being sine and cosine, u being cosine, sine being du, yeah, it does work out okay. Try. Keep trying different things just to see what comes up. All right, any questions so far? Kind of blah, 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 isn't it? So let's see what their rule is for oh, wait. Let me back up. This is this problem. Sorry, I forgot. I thought this was one they didn't have. Okay? Let's erase our ink and see what they do. Now, first, just like you said, do the double angle formula to get 2 sine x cosine x. Okay? So that's the first step. Pull the 2 on the outside. Okay? Now, at that point, nothing seems like it's going to be very helpful. For sine or cosine, nothing close to this shows up there. So what we do is consider a form just looking at the denominator. Again, find the most complicated part, which usually resides in the denominator. See if that follows the form. Well, it kind of looks like this form. Okay? A plus bu. If u was cosine and a was 1, a was 2 and b was 1. Well, the derivative of cosine is minus sine, so you've got a minus in there, and the sine, and this would be a cosine, which is u, du has a sine in it. So yeah, you've got just about what you need there. And there's your formula 3. I can't remember if I wrote it down or not, but I've erased it if I did. But that's what it turns out being. Plug in, let a equal 2, b equal 1, and u equal cosine x, and sure enough, your du is minus sine x dx, so you have a minus 2 out front, and the cosine x is u, and the sine x is du, so there we have, or minus sine x is du, so there we have pretty close to the form that we need, only they didn't show it as the form that we needed, and they just did a direct substitution in there, and you've got it. Now, one more step, and they distribute the minus 2 across the parentheses. I don't know why they haven't changed that to non-absolute value bars, because there's no way that could ever be negative. So, or 0 even. So I don't see any reason not to. And sure enough, that's the answer we got. So here's their little block here. I don't know what to call it. Substitute for rational functions of sine and cosine. For integrals involving rational functions of sine and cosine, the substitution u is equal to this thing is equal to tangent of x over 2. Right. Okay, sure. Like I remember that one. Okay. Wow. I'm pretty sure they're true, but wow. That's a real stretch. Okay? And if you do that substitution, cosine x, which you're going to solve for that, would be 1 over 1 minus u squared over 1 plus u squared times sine x. No, I'm sorry. That's what cosine x is. This is sine x, and there's your dx. Yeah, right. Okay. Now, I know where this is coming from. This is going back to the tangent of your half-angle formula, which is not one I use too frequently, but you can always look it up. And you do that substitution, and this is what you run into. And my word, I'm not about to memorize that or try to live with that. But it, if you need it, look it up and use it. And I'm sure that's what they're going to have us do. Oh, no. They don't make us do it in a problem. Thank you very much. Okay. That's just another little tidbit of information. If you find it useful, use it. If you don't, I wouldn't sweat it too much. Homework exercises 8.7. Do number 3. It's both at calcchat.com and calcview.com. Do number 5. That's at calcchat only. Do either 7 or 9. They're both at calcchat, neither at calcview. Do number 11 is at calcchat. Number 13 is at calcchat. Either 15 or 17, they're both at calcchat. 15 is at calcview. Then do any of the odds 19 to 39, they're all at calcchat, none of them are at calcview. Do any of the odds 41 to 47, they're all at calcchat, 41's at calcview. Do any of the odds 49 to 53, they're all at calcchat, none of them are at calcview. We didn't do any with arctangent, though they do some, but they're in the tables. Any of the odds 55 to 61, they're all at calcchat, none of them are at calcview. Do 63, it's at calcchat, not at calcview. Might give a look at 65. I don't know if it's at calcchat or not, but it's finding a pattern, which are always good things to look for. There is a sort of an applied example, number 67. Try to do that. It's at calcchat. And or the population problem, which is at 69. So one or both of those. Both of them are calcchat. There's another application problem, 71. So I'd say do any of the odds 67 through 71 and then move on. All right. Now, I don't know I don't have a real, well, let's move on here. The next section is called improper integrals. And frankly, if they're improper, I don't find too much practical value in doing them. Sure enough, you may run into them sometime or another, but it just doesn't seem to me to be super likely. And what I'm going to do here is just do a quick slideshow in case you ever need one of these things. You'll at least know where to go back and review, okay? But by and large, I'm not going to test you on these. They do have some rules and things like that, and that's what I'm going to show you. But in my mind, well, we just need to move on. So let me, 8.7. What I want to do is get out of this and move to 8.8. And again, I'm just going to do a quick slideshow. I think this is the last section in the chapter. So before you leave today, I'm pretty sure I have your test. Did I give you all your tests last time? Some of you did not. I'll check and see. I thought I had it made out. But let's take a look at this. Let's go from current slide. But like I say, I'm not going to be testing you on this, but I do want you to see it if you ever need any of these things. This is the improper integral part, and I kept saying we're really not going to do much with that. This is improper integrals. And if they're not proper, why do them? No, that's not quite true. Evaluate an improper integral that has an infinite limit of integration, which to me, I don't know when you'd ever run into that. And evaluate an improper integral that has an infinite discontinuity. And when would you do that? Either. But you might, okay? So let's do first infinite m limits of integration. Here's your definition of a definite integral. Of course we know it. Integral from a to b of f of x dx. Requires that the interval, not integral, but interval a to b be finite, okay? Furthermore, the fundamental theorem of calculus requires f of x be continuous on that finite interval. Now, it says here, you'll study a procedure for evaluating integrals that do not satisfy either or both of those, okay? Usually because either one or both of the limits of integration are infinite, or because f has a finite number of infinite discontinuities on the interval, okay? So, there's just something about it, it seems like it's enormous. I don't know. There was some movie that Betty White was in, and it had something to do with Facebook. And I remember she won an Oscar for it. And when she was in her acceptance speech, you can see I'm not a social media type person. In her acceptance, and she wasn't either. She said, you know, before this movie, I don't know if y'all know who Betty White is, but she's quite a good comedian. Old gal, and quite good. And she said, you know, before this movie, I didn't know what Facebook was. And now that I've done the movie, I've come to the conclusion it's an enormous waste of time. So, and that's what she thought of. And that's sort of what I think about this. If there is something that's here, it almost is an enormous waste of time to do it, because I don't think you run into that much. So anyway, let's go, and I'll get off of that. Integrals that possess either property are called improper integrals, okay? And if it's improper, I say, why do it, okay? But that's beside the point. Note that the function is said to have an infinite discontinuity at c when from the left or from the right, the limit as you approach the f of x, either from the left or from the right, is either a positive or negative infinity. So it doesn't have a limit. It has an infinite discontinuity. To get an idea of how to evaluate an improper integral, here's what they usually do. So for instance, the integral of from 1 to b of dx over x squared. Well, we know how to do this, okay? As long as x is not 0. If x is 0, all bets are off. You can't do that anyway, okay? But if it's not 0, then the antiderivative of x to the minus 2 would be minus x to the minus 1, so it would be this, okay? So minus 1 over x from 1 to b. And that would then, of course, be minus 1 over b minus a minus 1, which would be 1 minus 1 over b. Okay. Now, obviously, b can't be 0. You can't do that. But what if b was approaching infinity? Whatever that means. Well, 1 over b would be 0. So your answer here would just be 1. Okay? So it looks like you would be able to do that if b was approaching infinity. Okay? The integral can be interpreted as the area under the shade portion of this 1 over x squared curve here. And basically what it's saying is, if you're going from 1 here, this is going to 0 so fast, that has a finite area under it, even though it's an infinite x. Okay? I don't know what infinite x's are. I don't ever integrate to that. But sure enough, this would have an area of 1 under here. Okay? It's close to 1 here, and then that fraction gets so much smaller. So it does have, that's an improper integral, can be interpreted as the area of the unbounded region between the graph of 1 over x squared and the x-axis. And that does have a limit, and that is 1. Okay? Now, so your definition of improper integrals with infinite integration limits, that's what we're talking about now, going to infinity. If f is continuous on the interval a to infinity, which is not much of an interval to be, because it's unlimited, then what you can do is replace this integral with the limit as b is approaching infinity of integral from a to b f of x dx. If this has a limit, then this has an answer. The thing is, does that have a limit? Okay? If f is continuous on the interval from minus infinity to b, whatever that would mean, okay, you can replace the minus infinity with an a and let a approach negative infinity. Then if you can do this integral here, and when you plug in a minus infinity, you don't get something that blows up, then that integral works. And you can do it from both ends. If you're doing from minus infinity to positive infinity, split this into minus infinity to c, and of that thing, c to positive infinity, and take this limit for this one, that limit for that one, and see if you can go from there. In the first two cases, the improper interval converges when the limit exists. Otherwise, the improper interval diverges. In that case, there is no solution. In the third case, the improper interval on the left diverges when either of the improper integrals on the right diverges. So you can have one of these that converges and one that doesn't. The whole thing is lost. It will only be that both of them would work. Seldom will that happen. Just frankly, seldom will that happen. Okay, I'm not going to do this, but I'll tell you right off the top. Okay, just tell me, what do you think the integral would be? Integral of 1 over x dx. That's doable. What is it? Say again? Really? What's the antiderivative of 1 over x? Say again? What function when you take a derivative? Did someone say? ln of x. Yeah, that's a good old ln function. Okay? And that would be perfectly fine unless b was 0 or negative. Then you can't evaluate it anywhere. But if b was anything greater, log x doesn't converge, does it? As b goes to infinity, log x goes to infinity. So that would not have an answer as b is approaching infinity. Okay? Seems like they got this backwards. It seems like that should be an infinity up there, and then they do this, but they didn't do it that way. And the log rule is b approaches infinity, log x approaches infinity. That does not have a limit. Okay? So why do they put equals infinity? It has no limit. Don't say it's infinity. It just doesn't have a limit. Okay? An infinite limit is no limit. Okay? And that illustrates this. So just get the idea. You can't integrate from 0 to infinity 1 over x. It just doesn't work. Okay, what if you have infinite discontinuities? Well, here are the rules for that. In this case, if f is continuous on an interval from a to b, has an infinite discontinuity at b, so its integral is continuous, including a but not including b, has an infinite discontinuity at the b, okay, then you can take and replace the b with some c and let c approach b only from the left. Or if you have a discontinuity in a, but you can, it's continuous from a to b, but not necessarily at a, then you can take the limit, the integral from c to b, and let c approach a only from the right-hand side. See what you get. And then this, if it happens on both sides, then you go. But if you have a discontinuity, if you have an infinite limit anywhere, then the whole thing's off. Okay? Now, why didn't they just give you the rule to begin with? We did 1 over x and saw it doesn't have a limit. Now they're doing 1 over the cube root of x. Okay? Now, no problem when x is going to 1. Big problem when x is going to 0, right? You can't define, that's undefined. Okay, can you do the integral? Well, the x to the minus 1/3, write that in power notation. That would be this, and then take the limit as b approaches 0 from the positive side. Well, sure enough, it really doesn't have a problem here, does it? Because this is now in the numerator, it's not in the denominator. So that indicates you would have a limit. You would have a defined function there, as long as b is going to 0 from the right-hand side, not from the left of matter. And that would be b over 2. So cube root of 0 is 0. Okay, so that does have a limit. Here is, and this is the bottom line for all these. When you're going an integral from some value that is okay to some value that's not okay, if this p, remember we did it when p was a 2, it works. For any time p greater than 1, then this integral is going to come out being that every time. Okay? If p is less than or equal to 1, diverges, don't even try. So when 1, that didn't work. Anything less than 1, like 1/3, it didn't. But that's going the other direction. So that's the rule, and it's called, let's see, goodness, I have a name for it. I want to call it the P rule. I believe that's really what they usually call it, but I don't see it listed here. Okay. In fact, having trouble seeing how these slides are hanging together. Oh, here, I got it. They did skip one thing here in their skipping example 3. Do y'all remember L'Hopital's rule? Okay, that is one thing you can use here, and I highly recommend it, and I can't for the life of me figure out why they skipped that in the slide set. But L'Hopital's rule is given here. They really don't say a lot about it, but you can use that. Remember, that was for 0 over 0. It also works for infinity over infinity and other similar things like that. So this is your here it is. Special type of improper integral. And for the life of me, I can't think of what else. I think they just call it the P rule. And so remember that. And that's the only thing I do with infinite things. This rule here. If P is outside that, it's not going to have an answer. Now this is something called Gabriel's horn. And it's just a bizarre looking little function, and I'm not going to do any more than show it to you. But you use the disk method that we did before and just apply it to this. If you can do the integral, then the revolution you should be able to do as well. And, well, actually, let me take that back. You can't do this integral. Remember, that didn't have one. But when you do a revolution of it, that squares this. And when you square it, then it does fall within the P rule, and you can do the volume, even though you can't do the area, which is rather bizarre, okay? And anyway, that's what it comes out being. All right. So you can do the surface area. I said volume. You can do the surface area even though you can't do the area underneath the curve. Rather bizarre. Okay. Nope, you can't do the surface area. It's also infinite. Sorry about that. So why mess with it? Why did they even show it? Again, you don't need to do 8.8 or anything to do with that. There are review exercises at the end of the chapter. CalcChat.com still has tutorial help for worked out solutions for odd number exercises. So if any of these are beneficial to you, do them. 1 through 7, 9 through 15, 17 to 25, 27, 29 to 33. This is on page 583 and following. 35, 37 to 43, 45 or 47, 49 to 55, and I would stop there and not mess with the rest of them. Let me see if I got your test made out. I thought I did. I thought I had handed them out before, but may not have. Now this is test 2. Oh, I looked at that and says, how is someone turning it in? That was Cal 1. Okay. Let me find Cal 2. Here we are. Okay. Yeah. Test 2. Okay.
Now we need time for a break.
Yeah, it would be. Let me just go over this real quickly, though. Number 1 and 2 are from sections 8.1, I believe. Let me go back and find. Yeah. Okay. Just make sure I'm saying it right. Yeah. 1 and 2 are from 8.1. 3 and 4 are from 8.2. 5 and 6 are from 8.3. 7 and 8 are from 8.4, and 9 and 10 are from 8.5. That's why I thought I gave them to you before, because we had already done all that stuff before. I guess I just forgot about it. Or maybe it was last Monday, yeah. If we'd had class on Wednesday, I'd have passed it out, but we didn't. Okay, I heard a request for a break time, so let's take a quick one, less than 5 if you can do it, and then we'll come back and get started on Chapter 9, Infinite Series. Now, let me just say this, in case we're losing some people, which I think we might. We're only going to do 9.1 and 9.2 in Chapter 9. We're only going to do 10.2, 10.3, and 10.4 in Chapter 10. And then we're going to try to do as much as we can of 11.1 through 11.5. I don't think we'll get to 11.5 in Chapter 11, and that will be your last test, which will also be the final exam, which cannot be dropped. So you will be able to drop your lower of the first two test scores, but the test 3, which will cover 2 sections in 9, 2 in 10, and whatever we cover in 11. That will be the last test, and that will not be droppable. So that'll be the end of the term. All right. Let's take a quick break. Try to get back within 5, less than 5 if you can. treatment on Friday, and going into it, everything was low. Platelets, neutrophils, white blood cells, red blood cells, hemoglobin, hematocrit, everything were low. And then, of course, after the treatment, they went even lower, I'm sure. And so I'm just so tired. Fatigued is the better word because of the low red cells. And then, too, because of the low neutrophils, I think, it seems like after most treatments, I get conjunctivitis. I don't know why. That's where it shows up. That's where the low, neutrophils pops up in my eye. And so I am sort of squinting and red-eyed and that kind of stuff. And sorry if it's not too obnoxious. Okay. Well, we've got, I forgot to turn off the projection. Yeah. We recorded all that. Okay. So anyway, we're still recording. So all that dead time that you had in there. Sorry about that. I thought I had hit the thing, but I must not have. So we'll go from the current slide, and now we're looking at infinite series. Okay? And again, we're only going to do the first two sections here. And section 1 is talking about infinite series, sequences. Okay? It's talking about sequences. And we'll learn what a sequence is, and then a sum of a sequence is what we call a series. So that's what we're heading for. So we'll start with just sequences. And the 4 objectives we have here will first be to write the terms. Write the terms of a sequence. We'll determine whether the sequence converges or diverges. So back, same type of thing we were talking about with the infinite integrals, improper integrals, that kind of stuff. But now we're talking about sequences. We'll write a formula for the nth term of the sequence. To me, that's part of writing the terms of the sequence. And then we'll use properties of monotonic sequences and bounded sequences. We'll define both of those and see what we get. Okay? Hold on just a minute. I just to the floor before, and I forgot to pick it up. Okay. So let's start with just the term sequence. What in the world is a sequence? A sequence is defined as a function, believe it or not, whose domain is a set of positive integers. Positive integers. Okay, rather strange domain. Although a sequence is a function, it is common to represent sequences by a subscript notation where the subscript are those positive integers, okay, rather than by the standard function notation. So, for example, here's a sequence. 1, 2, 3, 4, 5, 6, 7, 9, up to n, and you can keep on going past n, okay? Those are your integers. The sequence that would be either this sequence or some other one, a sub 1, a sub 2, a sub 3, a sub 4, a sub n, and on like this. That would be your sequence of values, numbers, functional values. 1 is mapped onto A1, 2 onto A2, A3. See, the subscript here is just identifying which value in that sequence you're talking about. Okay? These are also called the terms of the sequence. The number a sub n is called the nth term. A sub 4 is the 4th term. A sub 17 is the 17th term. A sub n is the nth term of the sequence, and the entire sequence is denoted by this. That symbol there is called the brace. I don't know if you've run into this before. A sequence is defined denoted by the symbol, the brace with a sub n in it. Okay? It's the nth term in a sequence. The entire sequence is denoted by the braces over a sub n. All right? We're talking about what a sequence is. It's actually a function, but usually denoted by subscripted notation. The domain of the function is positive integers. Okay? So each term in that sequence, in that function, is represented by a sub n, where n is some integer. Okay. So, the terms of a sequence, a sub n, remember that represents the whole sequence, and this happens to be 3 plus negative 1 raised to the nth power. Okay? Now, let me get my pen back. Okay? Remember, your n represents integers. Okay? You could start with 0. Most of the time they start with, well, no, actually positive integers. They did say that. It's a set of positive integers. So it doesn't start with 0, it always starts with 1. Later we'll see it can start higher, but whatever. Okay? So, if this is your a sub n, then a sub 1 would be 3 plus negative 1 to the first power, which of course would be what? Say again? A little louder. Okay, negative 1 to the first, that would be 3 plus a negative 1. And what would that be? 2, right? A sub 2 would be 3 plus a negative 1 to the second power, which would be, second? Okay, well that would be 3 plus 1, which is 4. A sub 3 would be 3 plus a negative 1 to the third power, which would be 3 minus 1, which is 2. So you see the pattern? A sub 4 would be 4. A sub 5 would be 2. A sub 6 would be 4. Okay? So in other words, for every odd term, the next in the sequence is the value in the sequence is 2. For the even terms is 4. Okay? Now, without even defining it, do you think that sequence converges? No. It keeps bouncing back between 2 and 4, and 2 and 4, and 2 and 4, and 2 and 4. It's not heading anywhere. It's not going toward 2, it's not going toward 4, it's not going toward 3. It's not going through anything else. It's just bouncing back and forth between the two. Okay? So there's a sequence. Okay? Perfectly good sequence, it's just one that doesn't converge. Okay? Let me erase this, and I'll show that's 2, 4, 2, 4, 2, 4, 2, 4, on and on and on. How about this one? The terms of the sequence B sub n are n over 1 minus 2n. So B sub 1 would be what? One over 1 minus 2. And that would be negative 1. B sub 2 would be 2 over 1 minus 4. And that would be negative 2/3. B sub 3 would be 3 over 1 minus 6, is that right? And that would be negative 3/5. One more. B sub 4 would be 4 over 1 minus 8, which would be negative 4/7. Okay? And so on. Okay? Now, Those happen to be positive terms in a sequence. These happen to be negative. Okay? Anything special about these? Increasing, decreasing? Okay. The absolute value is decreasing, which because the negative numbers there actually be increasing. They're never going to reach zero, right? But they are increasing, so they seem like they would have a limit. Okay? Rather strange sequence, but definitely a sequence. So let me erase this, and we'll see how they did it. -1, -2/3, -3/5, -4/7, and so on. Okay? These are just sequences. Okay? How about this one? What would that be? C(1) would be, help me, 1/2 minus 1, which is 1. C(2) would be 4 over what? 4 minus 1, which is 4/3. C(3) would be 9 over, second, 8 minus 1, which would be 9/7. C(4) would be 16 over, second, 16 minus 1, which would be 16 over 15. C(5) would be 25 over 32 minus 1, which would be 25 over 31. Okay? Now, what do you notice about this one? Started at 1, went up, not quite as far up, so it started coming down, 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 and guess what? It keeps going down. Okay? So even though at first it seemed like it was an increasing sequence, now it seems like it's a decreasing sequence. I think that might have a limit. Well, a bit early to tell. I would say yes, okay? Because, and this is something you'll pick up somewhere else, that n squared is, even though it starts out being greater than n, after a while, 2 to the n far outstrips that, as you see, it's beginning to do here. And it's going to continue to do until it's getting quite large. Even though n squared is getting large, 2 to the n is getting extraordinarily large, and soon it's going to overpower it completely. And that limit, I think, will go to 0. Okay? It may take a while, but it will head that way. Okay? Now, let me erase that. Any questions on these so far? And that's 1, 4/3, 7/9, 16/15, and then they actually start getting, after 4/3 they start getting smaller, but they get quite a bit smaller. All right, now here's number D. These terms are of the terms of the recursively defined sequence D sub n. Notice the earlier ones only depended on n. Okay? The recursively defined sequence depends on not just what n is, but what the previous n was. The previous value was. Okay? And this is the sequence here. It's not quite written the same way the others was, so let's give a few terms there. Let's just start with, and they give you D1 is equal to 25. So what would D2 be? 20 is dn, d1, which would be 25 minus 5. So d3 would be 15, d4 would be 10, d5, 5, d6, 0, d7, negative 5, and so on. That's going small, smaller, smaller. Every time is decreasing by 5 until you get into negative numbers, and it just keeps decreasing. Not going to have a limit anywhere. Okay? So they only went through 10, but you see it just keeps going down. 25, 20, 15, 10, 5, 0, negative 5, negative 10, negative 15, and so on. Okay. That's a recursively defined sequence that depends on the previous term. Okay. All right. That's what sequences are. And I've already been asking a question, what is the limit of the sequence? And let's see if we can get that defined here. Okay? All right. The primary focus of this chapter concerns sequences whose terms approach some limiting values. And you've already noted I was pointing those out to you before. This doesn't seem to be converging anywhere like 2, 4, 2, 4, 2, 4, 2, 4, or that last one, negative 5, negative 10, negative 15, it just keeps getting more negative. Okay. Such sequences are said to converge if they do approach some limiting value. Here's the sequence. This is 1 over 2 to the n. What would be the first one? 1 over 2. The next one? Next. Next. 1 over 16, 1 over 32, 1. Okay. So yeah, that's what we got here. Okay. Now, look like they may be converging. Yeah, going towards 0. Because they're getting smaller all the time, but can never be 0, right? Because no matter what you got 1 in the numerator, that's never going to be a 0. But your denominator keeps getting bigger, 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 so you're getting closer and closer to 0. So yeah, that converges to 0 as indicated in this following definition. Let L be a real number. The limit of a sequence, A sub n, is L, written as the limit as n approaches infinity of A sub n is L. Okay? That's how we define the limit of a sequence, is that value L. If for every epsilon greater than 0, oh, it sounds like good old derivatives again, or Riemann sums again, or something like that. For every epsilon greater than 0, there exists some, now it's no longer a delta, some capital M greater than 0, such that for the absolute value of A sub n, whatever this is, minus L, okay, is always going to be less than that epsilon. Absolute value is going to be less than some positive epsilon whenever n is greater than m. So even though some of these may start out and start bouncing higher or lower or something, after a while they get into a range that you're never going to exceed. As n goes greater than m, that difference between A sub n and L will be less than whatever epsilon you chose. No matter how tiny you chose it, you can find an m out there that you guarantee from there on they're going to be less than that. Then the sequence converges to L. If the limit, limit of a sequence does not exist, then we say the sequence diverges. Even though it's not getting bigger, like 2, 4, 2, 4, 2, 4, 2, 4, it's not blowing up or anything, but it's still not converging, so it diverges. Okay. Negative 5, negative 10, negative 0, yeah. That's getting infinitely more negative all the time. That definitely diverges. But even 2, 4, 2, 4, 2, 4, or whatever. Okay. So, sorry, I'm getting hiccups. graphically, that definition says that eventually, for some n greater than some value, that given value m, and epsilon greater than 0, the terms of a sequence that converge to L will lie within a band plus or minus epsilon from L. Okay, L plus epsilon to L minus epsilon is shown here. Okay. For n equal 1, you're way up here. N equal 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But somewhere out here, you stay within this band L plus epsilon. Down here, no, nowhere close. But for a big enough n, m greater than n greater than m, your goal stay within that band of L plus epsilon and L minus epsilon. So that is going to have a limit of L. Okay. For any epsilon you choose. Now, remember the one that was 2, 4, 2, 4, 2, 4, 2, 4. If you chose an epsilon of 3, say, yeah, you can stay within that. But for any epsilon, no. Epsilon less than 1, never going to make it. Okay. So it's not just video epsilon. It says for any epsilon greater than 0, you can find some m that's going to work. And it does. Then that would exist. Sorry. And it converges. Okay. Now, I think I said this before all of you came back in. If I seem to be blinking and doing weird things with my eye, right now I'm hiccuping, but that's a different issue. But I had a treatment on Friday, and I started out with everything low: white cells, red cells, hemoglobin, hematocrits, platelets, neutrophils, everything was low, and then they got lower because of the treatment. And so I'm, number one, fatigued like crazy. Number two, that's why my eye is red. It seems like that's where it shows up. Conjunctivitis almost always in that eye will show up because my neutrophils are so low. So if I'm blinking and doing weird things with my head, that's why. I don't know why I'm hiccuping, but that's beside the point. Okay, so here's theorem 9.1. Limit of a sequence. Let L be any real number. Okay? Let F be a function of a real variable such that the limit as x approaches infinity of f of x is going to be that number L. Okay? If A sub n is a sequence such that this f of n is equal to A sub n, for every point positive integer n, then the limit as n approaches infinity of A sub n is equal to L. Now, first they started off with alpha function of a real variable, not just of a integer, any real variable. If this function, as x goes to infinity, the limit is that function is L, then you can find this. There is a sequence as long as f of n. Now the n is positive integers. If f of n is equal to A sub n, f of n is equal to A sub n for every positive integer n. That represents a sequence that converges. If this function converges to a limit L, then the sequence that you get from that converges to a limit L. And it might be so what, but that does have importance. Okay, so here we go. I'm so sorry, I can't quit hiccuping. Find the limit of a sequence whose nth term is this. Okay? Now, let's start the brute force way. A sub 1, that would be what? Second? 1 plus 1 to the first, which would be 2. A sub 2 would be 1 plus 1 half to the second, and that would be, which would be 9/4. Okay? A sub 3 would be getting nasty fast, isn't it? Second? Oh. Okay. Now, not the way to go, is it? Okay? Really somewhat difficult to evaluate there. Okay? Well, sorry. I'm so sorry. I can't quit hiccuping. What if we did this? Rather than A sub n, we call this f of x. Okay? And this f of x would be 1 plus 1 over x raised to the x power. Okay? Does that look at all familiar to anybody? They say go back to section 5.6, which that was Cal 1. And hopefully when you were in Cal 1, you may have run into this. Does anyone remember? This is e to the x. Well, not just e to the x, just e. Okay. It's basically e to the 1, which is e. And that is that number, because someone do this on a calculator. 9 divided by 4 is 2.25, right? And this one would be 64 divided by 27. 2.37. Okay, seems to be increasing, doesn't it? But not increasing by much. Okay? In fact, getting less of an increase each time. And does anyone remember what the number E is? 2.7, blah, 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 blah. Yes. And that is indeed going toward that number. Okay? So, yes. So since the function is going to E, so is the sequence. So it doesn't look like it. It looks like it's increasing. And it's getting messy, messy, messy really quickly, but it's still approaching a limit. And that limit is the number E. Now, there are several, okay, let's see how they did it. They may make it make a little more sense than what we just did by voila. Yeah, well, they said, you learned this. Yeah, sure, right. Of course you did. Sorry. Limit as x approaches infinity of 1 plus 1 over x to the x is e. So you can apply that theorem we just did sort of in reverse, and then this means that the limit as n approaches infinity of a to n is the same type deal here, and that's also e. Now, new subject here. There are different ways in which a sequence can fail to have a limit. Do y'all see something sort of flashing in this? Yes or no? Okay. Do you? A little bit? Okay, good. I was afraid I had a mic coming on because the lights are doing this to me, and I thought this is not good. But if y'all see this, okay, good. Thank you. Okay, that relieved my mind considerably. Okay. While I'm looking at that, I'm seeing strobing almost for you. One way is that the terms of the sequence increase without bound. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's no limit to that, right? Or they can decrease without bound. Remember the negative 5, negative 10, negative, decreasing without bound. Okay? These cases are written symbolically as shown this way. Terms that increase without bound, well, the limit as n approaches infinity of a sub n is a positive infinity, or for those like the negative, the limit as n approaches infinity of a sub n is negative infinity. Both of these are unbounded, diverging. There's several names you can give it. Okay? Now, the properties of the limits for a sequence, it seems like they're jumping all over the place here, just like the lights are doing. Which I'm afraid that means I have a bulb about to go, so that could be very expensive. Let the limit is n approaches infinity of a sub l be L. So in other words, we do have a limit. Now these are properties. Let's say that the limit is n approaches infinity of b sub n is also, it has a limit, and it's k. Neither one of these are infinities. These are numbers, okay? Now, first property of the limit of the sequence, scalar multiple. For any real number c, the limit as n approaches infinity of c times this a sub n is you can pull the c on the outside, and then you have the limit of this, and that would be c times l. So, guess what? No matter how big the c is, okay, c could be 3,487,000. If this limit exists and you multiply every term in that limit by an enormous number, or a small number, doesn't matter, it's still going to have a limit. It'll just be that enormous number or small number times the previous limit. Okay? Secondly, sum or difference. The limit is n approaches infinity of your a sub n plus or minus the b sub n. Okay? Two different sequences, you're adding them together. Then it'll be the limit of the first plus or minus the limit of the second. If it's plus, it's plus. If it's minus, it's minus. Now our product. The limit is n approaches infinity of a sub n. This sequence multiplied by another sequence is going to be the product of the sequences. So the limit of the product of the sequences is the product of the limits of those sequences. And quotients, same type deal with one little exception. The limit is n approaches infinity of a sub n divided by b sub n. So the limit of the quotient of two sequences is the quotient of the limits, as long as that bottom, the denominator, the one on the bottom, is not equal to 0, and the k is not equal to 0. Okay? Otherwise, it makes no sense. Sorry. All right. How much longer do y'all have to endure hearing me hiccup? Okay. This really seems to be jumping all over the place. Okay? It's just getting your terminology down. But before we go there, let's do examples 3. Okay? And example 3, even though it's not on the slide set, you can go to larsoncalculus.com and see an interactive version of this type of, Let's type in an example. Okay, let's do example 3 here. Here's a sequence. Three plus a negative 1 raised up to the nth power. We saw something very similar to this. In fact, this is the first one we did, wasn't it? Okay. What's that? It is the same one. And what was it? 2, 4, 2, 4, 2, 4, 2, 4, dot, 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 dot. Okay? Now, that limit exists? No. Okay. Sequence diverges. Even though it's not blowing up or anything, it's still diverging. Okay. How about this one? I think we've seen this one too, right? Okay, what would that be? When it's 1. Oh, what was that? Okay, 1 over a negative 1 would be negative 1. So that would be negative 2/3. Okay, remember that one? Right, is that right? Okay. Now, what do we decide about that one? Does seem to be converging, and converging to what? Let's pick a big number. Okay? Pick a big number like 30. Okay? 30 over 1 minus 60. That would be 30 over 59, right? Huh? Negative, yeah. Okay. So that would be getting awfully close to negative 1/2, right? And sure enough, it seems like that's where it's heading. Okay. And that's exactly where it's heading. Negative 1/2. That does have a limit. It converges. Okay. That's all they did. I thought they were going to do some combinations of that, which I thought, how can you do that? But you can't. Okay, that was example 3. Let's do example 4. Okay. Any questions before I delete it? Sorry. All right. Now we're going to go back to L'Hopital's rule. We hadn't done anything with it, but we're going to now. Sorry. Show that the convergence, that the sequence whose nth term a sub n is equal to n over, n squared over 2n minus 1. Okay? Show that it converges. Now, we picked out numbers and looked at them and said, yeah, after a while, that sure looks like it's getting smaller and start getting smaller much faster. But how in the world can we show this? Well, one way, remember, we can change a sequence to a function. What would be your f of x then? X squared over to the x minus 1. Okay? And we could let this x go to infinity. Okay? Now, what we're then wanting to, oops, that's an x there, not an n. What we've got then is the limit as x approaches infinity of x over 2 to the x minus 1, right? Now, do you recall how you can evaluate a limit like that? That's going to infinity over infinity, obviously, right? Second?
Derivative? You take the derivative?
Yes. L'Hopital's rule. L'Hopital's rule said take the derivative of the numerator, take the derivative of the denominator, and see what happens. That would be the limit as x approaches infinity of, and what's the derivative of the numerator? 2x, derivative of the denominator. Ah, okay. Yeah. It's the ln of 2 times 2 to the x. Okay, I want to make sure. Yeah. Okay. Now, I don't know if you remember that. Okay. It's a rather bizarre way to go about doing this, but it's certainly able to be done. But that is what you get when you take the derivative of that. Now, that's still going to infinity, over infinity. So guess what we do the next time? Take another derivative. That'll be the limit, if I could write, as x approaches infinity, of, and what's the derivative of the numerator? 2 over, and whatever it turns out being, I think it's ln 2 squared times 2 to the x or something like that. But guess what? That limit, as x goes to infinity, is going to 0. So if the numerator is fixed, that's getting very big, very fast. I think I did it right, but let me see. Yeah. Okay. And that is going to 0. So the limit does exist. So quite often, for something like this, it's very hard to show in a sequence. Get it to the functional form, and then even if you can't evaluate it, but if it's a form like 0 over 0 or infinity over infinity, and actually there's one that's infinity minus infinity, L'Hopital's rule will work. Just keep applying it until you either get something you can evaluate or something that blows up. And that will tell you whether it's going to be converging or not. Okay? So that one's going to 0. And that's what we saw when we did a few terms and said, yeah, the numerators are going up sort of fast, but the denominators are going up really, really fast, so it's going to 0. All right. Now, new topic. I don't know if it's new to you or not. Are y'all familiar with factorial notation? What does that mean? Okay. Yeah. Okay. N factorial would be, give me a number for n, any number. 5. So 5 factorial would be 5 times 4 times 3 times 2 times 4. Well, times 1 is not going to do much for you. But that's what it is. That's what a factorial is. Whatever the number is before the factorial symbol, and the factorial symbol is the exclamation point. Okay? So don't be surprised with it. You know, that would be, and they're actually listing it the other way. I always think of it as counting down. They're counting up. It doesn't matter. 1 times 2 times 3 times 4 times 5 times 6 times 7 times whatever the next to last number is times, you know, whatever that would be. Okay? Now, here is a bizarre thing. 0 factorial is still 1. 1 factorial obviously is 1, right? 1, 1. Okay. 0 factorial also has to be defined as 1, even though that makes no sense by your definition. But 0 factorial is 1. Okay. Other things that make no sense, usually they don't have, like 0 to the 0th power makes no sense. So that doesn't have a definition. 0 factorial does. From that definition, you can see that 1 factorial is 1, 2 factorial is 2, 3 factorial is 2 times 3 is 6, 4 factorial is 6 times 4 is 24, 5 factorial is 24 times 5 is 120, whatever it is, okay? But you just keep on, and they increase pretty quickly, okay? After the first few, they increase quite quickly, okay? Factorials follow the same conventions for order of operations as exponents. Okay? Rather bizarre statement. That is, just as 2x cubed and 2x cubed are not the same thing. They're different order of operations. So 2n factorial and 2n factorial are very different. This would be 2 times n factorial. If n was 5, that would be 2 times 5 times 4 times 3 times 2 times 5. Whereas this would be, if n was 5, that would be 2 times 5 is 10. That would be 10 times 9 times 8 times 7 times 6 times 5. Okay. So very, very different numbers. Okay? Yeah, and that's what I just said. I just threw in the n of 5 because that's what we had used. So this would be 2 times n factorial. And this would be 2n factorial, which would be whatever your n was, double that, and then I think of counting down, they count up, multiply up. Much different number. This is much larger number than that. Okay. Okay. Another useful, let's see, I think we have time for it. Another useful limit theorem can be written in for sequences is the squeeze theorem. Okay. If the limit as n approaches infinity of a sub n is some limit L, and that's also, by the way, the limit for b sub n as n approaches infinity. And there exists some integer capital N, not anything to do with little n, such that a sub n is less than b sub n, but somewhere in between there's a c sub n, in between that for all n greater than this capital N, then the limit of c sub n also has to be like L. Okay? So in other words, if a sub n is coming down and has a limit of L, and b sub n, however it's doing, has a limit of L, and there's some other c sub n that's between a sub n and b sub n everywhere, then at some point it's got to have a limit of L too, because it's c sub n is greater than a sub n, but less than b sub n. But both of those are converging to L, so therefore C has to as well. The squeeze theorem. And that leads up to example 5, and I think that also leads to not enough time to do it. Also, we'll begin next time with example 5. No, example 5. On the wrong page. Let's see, did we get far enough for some homework exercises? Hopefully so, don't you think? Okay. 9.1, I think you can do any of the odds 5 through 9. They're all at Calc Chat, 9's at Calc View. I think you can do 11. It's at Calc Chat. You can do either 13 or 15. They're at Calc Chat, not at Calc View. And then, let's see. I think you should be able to do 17 and 19. We didn't do anything like them, but I don't see any examples like them. So try to do those two. And we'll pick up there next time. Okay? So, any questions? Good deal. All right, let's end this. Everybody got a copy of the test, right?